For number 28, it's kind of like the other Hess law problem, but you're dealing actually with less complex information. So you're just taking one of those steps and seeing if you can turn it into another equation. So what we're noticing here is let's just map out all the species. So we have SO2 on the left and it goes to the right up here. Okay, so let's see if other things are going to make sense. Oxygen's on the left, it goes to the right, and then sulfur trioxide's on the right, and it goes to the left. The reason I'm going from the bottom to the top is because we actually know this information. So far, the first thing I found just now is that everything flips sides. Remember, when everything flips sides, you flip your sign. So in this case, we have a negative sign. We need to turn our negative sign into a positive sign. So that would just make it, so far, a positive 98.4 kilojoules. But that doesn't seem to be the only thing that happened, because when the sulfur dioxide moved to the left, or when the sulfur dioxide moved to the right, I should say, the 1 coefficient became a 2 coefficient. Turns out, if you notice, everything actually doubles. So this 1 became a 2, and oxygen's half became a solid 1. So not only did everything flip sides by going to the other side of the arrow, but everything doubled. This means you need to take that 98.4, and with sig figs, it becomes 197 kilojoules. That's going to be the heat of the reaction. So that's really just like Hess's law, but simpler, because you're just looking at one part and seeing if you can manipulate and flip and turn things. If you can do Hess's law like in 25, you should be able to do 28. It's simpler than that. 29, yes. And then 30. Consider the following reaction. Okay, this video is way shorter than the other one, the last one. So consider the following reaction or equation. We have sulfur and oxygen creating sulfur dioxide with this heat evolved. So this is exothermic. Which of the following is true? Oh, well, there we go. This reaction is exothermic. That is true. This reaction is exothermic because we can see that this is a negative sign. So negative sign means it's exothermic. It's giving off that amount of heat for every 1 mole of sulfur that is burned. When 0.5 moles of sulfur is reacted, 148 kilojoules of energy is released. Who knows? Let's figure it out. Let's do a little bit of basic stoic. 0.05 or 0.500 moles of sulfur. We're going to do a basic proportion. We're going to convert our moles of sulfur into kilojoules of energy. We have a big invisible 1 in front of the moles of sulfur, and we can just use this from our equation, 296. And it looks right. 296 divided by 2, basically 148. Good to go. That one makes sense. And then the last one, it says it's true. We see the answer here, but let's see why. So 32.0 grams of sulfur, convert that from grams of sulfur to moles of sulfur, and then just like we saw, convert our moles of sulfur into kilojoules. For this first part, we use the molar mass of sulfur, which is, I don't know. Let's find out. Sulfur has a molar mass of, that's the wrong periodic table, 32, basically. So those basically cancel out. And then for every 1 mole of sulfur, you have 296 kilojoules. So let's do our math here. Something's looking off. Oh, yeah, there we go. So when we do our math here, we get 296 kilojoules. So that kind of makes sense. But notice how this is joules. So we just need to convert from kilojoules to joules. 1,000 joules is a kilojoule. And then basically do 296 divided by, multiplied by 1,000. And then it's basically just, do you remember how scientific notation works? Because this looked almost false. I almost thought it was false for a second. But then I realized, oh, that's going to give me a big number, 296,000 joules. And then doing scientific notation, I get 2.96 times 10 to the 5th joules, which does make sense. So all of those statements are true. Hopefully that helps.